Good day everyone, my name is Jose Alberto Luzardo, also known as HAL, and in this video I'm going to talk about object-oriented programming in embedded systems. Up to what extent? As always, I have my automaton assistant helping me on this presentation. His name is Carl 2017.6. He went from 0.5 to 0.6 since I fixed a bug he had. He was calling me David. Hello, Carl 2017.6. Could you tell me what is my name?
Your name is Jose Alberto Luzardo, also known as Hal.
That's good. I'm not David anymore. And what is your name?
My name is Carl 2017.6, but since my revision name is changed every time bugs are fixed in me, you can call me Carl.
Perfect. Should we begin, Carl?
Certainly. This presentation deals with the general aspects of OOP to assess its values developing firmware for embedded systems. We will do so by weighing those values against software engineering best practices. First, we review the software development life cycle and software engineering best practices. Then, under this software engineering context, we will try to determine the suitability of object-oriented design and functional or procedural design, such as that described by structural analysis, and we will describe the advertised OOP features we can find in any OOP textbook. Finally, we separate design techniques from programming languages to establish our conclusions. Let's then talk about the software development life cycle.
The first thing that comes to mind when we hear the words software development life cycle is the waterfall model.
I do not think software engineering really means this waterfall.
Oops, I think you are right, but you cannot deny that this one is very refreshing.
It will not be good for my circuits.
This is the real waterfall model we need to talk about. The most important thing to say about this model is that practice and experience has made this model evolve. The idea of waterfall hints that one phase must follow the previous one, that only when a phase is over we should continue to the next one, but this is very impractical for software development, where functional code is the final product. It is natural that as we start working on our project we understand more of it. Design could bring up new requirements. Remember the maxim, requirements do change. Coding could improve the design, and so on. In other words, the real development is iterative and incremental. It is incremental because different parts of the project are developed in parallel following the entire cycle, all the way to testing and validation. In an incremental and iterative development, chaos can arise, such as lack of planning, lack of documentation, lack of order and priorities. We need to discipline ourselves for this not to happen. There are several methodologies that tackle this issue. The rational unified process is one of these methodologies. Notice in this figure how phases are done in parallel. Agile is another methodology for iterative and incremental software development. Here we can see how the entire cycle is applied to different components of the software and then integrated one by one in the whole system.
We proceed now describing the best practices of software engineering design. Software design is based on four principles: abstraction, information hiding, structure and modularity. Abstraction is the capability to determine the common attributes among objects seemingly different. Useful to sort, classify, and organize based on those common attributes. Information hiding refers to the fact that modules hide their implementation details and irrelevant data and communicates through well-defined interfaces. Structure is the mechanism to divide and conquer. It allows the decomposition of a large and complex system into smaller, more manageable components with well-defined relationships among themselves. Modularity is the result of the previous design pillars: abstraction, Information hiding and structure. A module is a software unit with a well-defined purpose that requires a specific data structure encapsulated in the module. A module can be separately compiled and stored in a library. A module could potentially be reused in other applications. The module design principle is, modules should be loosely coupled and highly cohesive. That is, modules should have, a, the weakest coupling and, b, the highest cohesion, ideally. The strength of coupling between two modules depends on the complexity of the interface between them. The weakest, ideal, coupling occurs when the interface exchanges data. This way, a change in a module is very likely not to affect the other module. Ideally, internal changes in a module should not affect other modules as long as the interface remains the same. The internal cohesion of a module is measured by the strength of the binding among its internal components. The strongest cohesion, ideal, is guaranteed when the internal components of the module works tightly together to achieve one purpose or goal. In this case, it has a well-defined functionality and a data structure encapsulated in the module. Our next point is to compare OOP and structured analysis.
Cal, now that we have established the context of software engineering and know what good software design should be, which methodology you think is better to design software, OOP or structure analysis?
I do not have a conclusive answer. It is like asking me, what is the best way to join two pieces of wood, a hammer and nails, or a drill and screws? I cannot answer that question without knowing the application. The only thing I can say is that any methodology that allows the software engineering best practices will do the job.
I agree with you on that respect, and we should say so. The best practices of software engineering design are independent of the programming method. However, it's not uncommon to find OOP proponents stating that structural analysis is not adequate to design software.
Those statements could be extreme because we know that software engineering concepts were developed in the 70s and 80s under the framework of structured analysis. For example, we have these two references. A good software design relies on the programmers, their discipline, their programming experience and their SE knowledge. In other words, to achieve a good software design does not depend on whether the software is organized around objects or around functions, but in the discipline and dedication of the designer/programmer to verify that all the software engineering attributes of good software are satisfied.
We could even say that both methodologies are quite equivalent.
We need to differentiate between the programming methodology and the programming language. A language could be more suitable than other to apply the software engineering standards. A language can also be made to suit a particular methodology over the other. These remarks are important to understand that programming methodology and programming language are two different things. The features of a programming methodology should be independent of a particular programming language. Our next point in this presentation is object-oriented programming featured advantages.
The object-oriented programming is based on objects and on how they communicate with each other to achieve a given functionality. According to OOP, the objects reflect real-life objects involved in the application, and that for this reason OOP is more natural. However, it's not uncommon to see no real-life objects in OOP programs. On the other hand, procedural programming is based on the procedures, functions, and on the data usage to achieve a given functionality. Objects are instances of a class or type which gathers the main attributes of the objects.
I understand then that OO has flipped the coin to focus on data rather than procedures. Data and functions always go together. What are the advantages of flipping the coin?
Let's continue to find out. OO main attributes are the following: abstraction, encapsulation, inheritance, polymorphism, modular reusability, and extensibility. The last two are a consequence of the first ones.
We know that abstraction, data hiding and modularity are best practices of software engineering. Previously, we have concluded that procedural analysis can also guarantee those attributes.
Yes, we have. The concept of a class covers both abstraction and encapsulation in OOP. A class is an abstraction of objects of the same kind that binds together data and procedures. A class has a public interface given here by the public functions and other data and function members that remain hidden from other modules. A class is the essential unit for OO modularity.
I can see how this definition is very convenient and enforces software engineering best practices. But I have a question.
What is it?
Who can guarantee that this class is an object class, as opposed to a functional class? In other words, was this class really abstracted from a set of objects that exist in the application, or from a needed functionality?
What do you mean?
The line between functional abstraction and data abstraction could be very blurry because functions and data always go together, two sides of the same coin. Do objects generate functionality, or does functionality determine the objects? What I am saying is that a developer could be thinking that he is creating a class of objects, when in reality, he is creating a functionality abstraction where he encapsulates all the data he needs for that functionality to happen. In the latter case, he would be doing procedural programming instead of object-oriented programming.
I didn't know you were a philosopher.
I am an automaton who thinks logically.
Certainly. Inheritance is the process through which a subtype class can be created from a type class. The subtype class inherits the public and protected attributes of the type class. In the figure, a graduate student is a student also, and all the attributes of a student such as name, GPA, courses, etc. are also attributes of a graduate student. And all the operations we can do with a student we can do also with a graduate student. This means that the student class makes no difference between a graduate student object and a student object. We can access the operations of the student class with either object.
This is a nice feature in the sense that a subtype class adds new functionality and expands the student data structure without modifying the original type class. Let us remember that every time we modify an existing, working code we open the doors to bugs. In actuality, we could say that we adapted the student class to a new requirement without modifying it. We can say too that we are reusing the student class, not reinventing the wheel can save time.
We could have also created a new graduate student class that accepts student class objects as part of its data structure. In this case, the graduate student object is not the student object. The graduate student object has a student object in it. Furthermore, we cannot access the operations of the student class using a graduate student object. For the sake of comparison, I would like to ask you this question: is inheritance an attribute of procedural programming?
Inheritance is an interesting name. I would like to put inheritance in a different way. We have a core module with its own data structure and functionality. Assume that a new requirement comes and we need to implement a new functionality that requires the data and procedures of the core module. The new module then is a superset of the core module, it includes it. The new module does not need to modify the core module, it just uses it. We just write the new functionality and set the new additional data. What is not procedural programming in all of this?
But how can I use the core module operations using an object with the new additional data structure?
The answer of your question does not have to do with programming methodology. It has to do with the compiler feature. What makes this feature an exclusive object-oriented programming attribute? I see the convenience of accessing directly the core module operations using the new object type. The main reason is, operations using the core type need also to operate with the new expanded type. In this case, I will purchase the right compiler. Let us remember again that compilers and programming languages do not make the programming methodology. I would like to summarize what we have discussed in order to understand the next OO feature. Here we have a core module, which is a subset of a bigger set indicated here as expansion 1. If we indicate the right compiler that the module expansion 1 is an extension of the core module, then the compiler can make the core module accept objects of expansion 1. This is good. I do not think that this has to do with genetics, but I know it makes the code reusable and more manageable. In this case, the compiler takes care of something that we do not have to deal with. We could have also more extensions of the core module, like expansion 2 and expansion 3 in the figure. We can see how any object from the core and the expansions can access the public functionality of the core module. Each extension has its own reason to exist. They have different duties to perform besides those encapsulated in the core module. The expansion modules execute these operations through their public interfaces and corresponding objects as shown in the figure. Sometimes, the expanded modules have a common operation, but they require different implementation for it. For example, consider an application where we want to read physical variables from the real world, such as temperature, flow, speed, position, etc. Each variable comes from reading an analog digital converter, ADC. A calibration operation transforms each ADC value into the corresponding physical units of the variables. We have one common operation, calibration, with many possible implementations. As a common operation, we could think the core module should have the implementation of this operation as a public interface, but this is impossible because there are many implementations for this operation. However, we could think that the core module can have a public placeholder as an interface that dispatches to the right implementation based on the type of the object as discussed before. This is done at runtime, and the way to do it is using function pointers. Notice that I have not mentioned the word inheritance or any word from the Greek lexicon. I put everything within a procedural programming context just to show that the equivalence of both programming methods is real. In the OO jargon, this is called polymorphism, and it is explained using inheritance as seen in the figure. The word virtual in the type class says that calibrate has no implementation in the type class. A compiler that supports polymorphism may create a function pointer table to discern, based on the type of the object, where to jump to run the calibration. A template is a generic programming tool. It creates a unique and reusable code that is type independent. A template is a blueprint that allows us not to reinvent the wheel, not to rewrite a new class or module just because its parameters change their type. Templates make easy to reuse previously coded classes and modules. The typical example of finding the maximum of two numbers can illustrate this. Thanks to the template, it is not necessary to write separately a max function for double and a max function for int. By replacing the template type t with the real type as indicated by the template, the compiler will generate the corresponding function at compile time. Unlike virtual functions that are resolved at runtime, Late binding, the templates generate functions and classes at compile time. Early binding. Templates are ideal to handle containers, stacks, lists, vectors, arrays, etc., where the handling of the container has a unique code regardless of the container variable type. See STL, Standard Template Library. Templates are a language tool that increases reusability regardless of the programming methodology, object-oriented or procedural programming. We proceed now with the last 2 points of our presentation.
In this presentation, we have tried to clarify some aspects of object-oriented programming, especially the way OOP proponents present it in relation with procedural or functional programming. Within the context of software engineering, OOP is a programming methodology that allows us to design the structure of a software system. So is procedural programming, PP. The structure leads to modules, what we call the divide and conquer of software engineering. Within the context of software engineering, modules are the result of abstraction and information hiding, and ideally they should be reusable as we expand the software. Not only OOP, but also functional programming can guarantee these attributes of software engineering. The quality of a modular structure is measured through how cohesive and decoupled its modules are. The real core difference between OOP and functional programming lies in the paradigm of object versus functions. Should we structure a software system based on an abstraction that comes from its functionality or from its objects? We all have a clear idea of what a function or procedure is, but the idea of an object in OOP needs more elaboration. According to OOP, an OOP object reflects a real-life object. Objects send messages to other objects, and they cause other objects to do operations. In reality, these operations are functions or procedures, and the objects are the data structures these functions operate with. Functionality and data are the sides of the same coin. We cannot separate them. To determine a module based on the right coupling between function and data is and has always been the challenge in software engineering. We for sure could conclude that a good OO software design should lead to a good functional software design, and vice versa. In other words, OOP and functional programming should meet at the optimal point as we improve their designs. Both methods are equivalent.
Contrary to what OOP proponents claim, there are indications that functional analysis is more intuitive than object-oriented analysis. I would like to cite 2 works on this respect. From the paper Comprehending Object and Process Models, an empirical study we quote. Proponents of the OO modeling approach argue that it lends itself naturally to the way humans think. However, evidence from research in cognitive psychology and human factors suggests that human problem solving is innately procedural. Given these conflicting viewpoints, we investigate empirically if OO models are in fact easier to understand than PO models. Results show that for most of the simple questions, no significant difference was observed insofar as model comprehension is concerned. For most of the complex questions, however, the PO model was found to be easier to understand than the OO model. From the second paper, A Comparison of Structured Analysis and Object-Oriented Analysis, an experimental study, we quote. Results show no significant difference in the time required for developing or maintaining a software application by applying those 2 techniques, whatever is the order of their application. However, we found 2 major tendencies regarding object orientation. 1, it is more sensitive to subjects' peculiarities, and 2, it is able to provide some reusability advantages already at the analysis level. The expression "it is more sensitive to subjects' peculiarities" confirms the idea that in OOP there is no clear path to object identification. Even though OOP proponents claim that the objects reflect the objects of real life, which is true for the obvious ones, experience indicates that objects depend on the software designer peculiarities, whereas functionality, which is directly linked to the goals of the system, is more objective. Something else to bring to our attention is the fact that all analysis starts with an understanding of what the system should do, requirements, and how the system should do it, that is, what the processes are to achieve the goals. This shows a natural human condition to understand first a system by its functionality, regardless of what objects the system needs to satisfy the requirements. OOP brings only two new concepts that were not standard in software engineering: inheritance and polymorphism. In this presentation, we have explained these concepts within a functional programming context to demonstrate that both concepts are not foreign to functional analysis. In this presentation, we have also insisted on the separation between programming languages, such as C and C++, and the programming methodology. It is common to find developers who believe that you can do more software engineering best practices with OOP than with procedural programming because C++ has those features. C++ was created with object-oriented programming in mind, hence the words class, inheritance, and polymorphism. If you replace them by module, module expansion, and multiple implementations by a single interface, you would have the corresponding functional equivalent, as explained in this presentation.
C++ evolved from C to be a new program language. It is as if C++ forgot its humble cradle. The plus is not a fair description since it is not an incremental step from C. C++ had definitely more features assisted by its compiler to enforce good software engineering practices, but is more complex and has a heavier notation than C. C instead has an effective legendary simplicity, so simple that it lends itself to spaghetti code. Shame on it. Where is the midpoint? How can we enjoy the programming simplicity with the assurance of a nice compiler? Nowhere. Well, SDLC went to learn how the work of Jacob Navia has led to a C with many C++ features, without the C++ complexity. In order to use C to guarantee information hiding and modular expansion, the programmer has to develop self-discipline. Not that a C++ developer doesn't have to do it, and know certain tricks of C. Using opaque, incomplete structures and pointers and function pointers, information hiding and modular expansion can be achieved using C. This is material for an upcoming video.
OOP is well equipped for applications that require high levels of abstraction and have high variability. GUIs and desktop applications like the one I'm using now are of that kind. Nonetheless, many embedded systems are very concrete, complex on the nature of the algorithms that are implemented, but concrete on the application itself. The levels of abstraction are lower in most embedded systems. For example, a hard disk drive needs 3 very specific control systems: spindle, seek and track following. Is it worth abstracting these 3 controllers into one just because they are controllers? Now, think about a SCADA or SDC systems. In these systems, there is a high level of variability because these systems must control and monitor a vast number of different physical processes. In this case, there are no specific control systems, but many types of them. To design for many types requires higher levels of abstractions. Embedded systems interact closely with the hardware and are in charge to program it. The traditional approach to solve this dependency is to create a hardware interface, API drivers, for the higher levels to communicate with the hardware. This interface needs to be well abstracted, so the higher levels need no modification when the hardware changes. Usually this layer is written in C, sometimes assembly language. For embedded systems, the consensus seems to indicate that there are no clear advantages of OOP over procedural programming, especially if we consider concrete embedded applications. Software engineering best practices are necessary in any embedded system always. The developer can use either OOP or procedural programming to design following software engineering best practices, and program their design using C++ or C++ with the compiler support to implement it. As the variability of a system increases, demanding higher level of abstraction, OOP, and C++ are justified more clearly. We are convinced OOP and procedural programming are equivalent methodologies. One should lead to the other one. After all, function and data are inseparable. A good OOP design should lead to a clear functional structure. Conversely, a good procedural programming design should lead to a clear object structure.
In this presentation, we highlighted the intertwined nature between data and procedures. We try to convey the point that object-oriented analysis and procedural analysis are not at odds with each other, although it has been presented like that through the years. Even for those heavy concepts of object-oriented analysis, we have found that they fit perfectly in a procedural context. Software engineering best practices should be the framework for embedded software design. Functions and objects will follow naturally. If you like this video and think it brings something new, please let me know through my website below. Find also the references used in this presentation in the description below. Thank you for watching and do not forget to subscribe if you are interested.